Welcome to our discussion on how to estimate a population mean. In this section we're going to look at techniques for estimating the population mean based on statistics we get from our sample. As always, we're going to have a best point estimate. In this case it's going to be the sample mean designated by x bar, and that's going to be our best point estimate of the population mean, shown here as mu. We'll see techniques for constructing confidence intervals, for giving us a more accurate estimate of the population mean. And then we'll also talk about ways to determine how large of a sample size we need to collect in order to get that population interval down to a certain size. In order to run the procedures that we're going to discuss in this lesson, we need to make sure that our population is normally distributed. So we're sampling from a normally distributed population, or that our sample size is at least 30 or bigger. And that's going to be a pretty standard requirement for most inferential statistics. Just like other confidence intervals, we're going to have a margin of error. This one has a relatively simple formula where our margin of error, again represented by an uppercase script E, is simply some t-score, right? So instead of z-scores, we're now going to be using t-scores, and then this s is the standard deviation of our sample, and then of course n is our sample size. And when dealing with t's, we have to have degrees of freedom. We have to know what degrees of freedom are, and in this case the degrees of freedom is going to be n-1. You can find t-critical values listed in tables and online, and most technology can give them to you as well. So what is this t distribution thing that we're talking about? Where do we get these t-critical values? Well, if a distribution is close to normal, then we get this t-distribution. It's called a student t-distribution, or more simply just put a t-distribution. And you'll notice that this formula is awfully similar to the z-score formula, which was x bar minus mu all over sigma. And then we had the one where we were looking at multiple. Right, when instead of just picking one thing, it was the z-score for a group of items, and then it was x bar minus mu all over sigma over the square root of n. Well, look at the difference. The only change is s instead of sigma, right? So when we don't know the standard deviation of the population, we have to use a t instead of the z. The z is only good when we know the standard deviation of the population, which is actually very rare. So it's far more likely that you'll be using a t-test or a t-distribution than z's. Degrees of freedom, it's just the number of sample values that are allowed to vary after you place certain restrictions on your data values. It's normally abbreviated by df for degrees of freedom. And for this method, we're going to let n-1 be the degrees of freedom. Now, other statistical procedures that we'll look at later, two-sample t-test, chi-squares, things like that, have slightly different degrees of freedom formulas. So just know that it's not always n-1, but n-1 is pretty standard and popular for a lot of degrees of freedom measurements. Typical vocabulary, you've seen all these before, the mu, the x bar, s being your sample standard deviation. The only thing that you haven't seen before is your t-critical, but you've already seen z of alpha over 2. So this is the same exact idea, only now we're doing it on a t-distribution instead of a z-distribution. Just as we saw before when we were trying to do confidence intervals for our proportions, we can now do a confidence interval estimate of the sample mean using the same idea, only instead of the p hat minus e and the p hat plus e, we're using x bar because we're now dealing with the mean instead of the proportions. In order to construct these confidence intervals accurately, there are certain requirements that we have to watch for. Right? We have to make sure that all those requirements are satisfied, namely that we're sampling from a normally distributed population, or our sample size is 30 or above. We use n minus 1 degrees of freedom, and we use that to determine the critical value of our t of alpha over 2. You create your margin of error, you add and subtract it to your x bar, that's the sample mean, right? And then you round to the appropriate digits, or you let technology do it for you. Here's an example. A common claim is that garlic lowers cholesterol levels. So to run a test of the effectiveness of this claim, 49 subjects were treated with doses of raw garlic, and then their cholesterol levels were measured before and after the treatment. The changes in the levels of their LDL cholesterol had a mean of 0.4 and a standard deviation of 21.0. Now, right off the bat, you should be thinking, this is some bad statistical reporting, because is that mean change of 0.4 mean that it went down by 0.4 or up by 0.4? Can you see how that would make a big difference? Because you're trying to claim that garlic lowers their cholesterol level, so if your sample of people actually went up, that would be a problem. So I would assume that it went down just based on what we're trying to prove, but a true statistician would report this a lot better, a lot more clear. So we can use our sample statistics of sample of 49, mean of 0.4, standard deviation of 21 to construct a 95% confidence interval estimate of the actual mean net change in cholesterol levels, for the entire population. And then we can interpret that. So here's how we do it with formulas and things like that. Are the requirements satisfied? Well, you assume we had a simple random sample. N is 49, which is greater than 30, so we don't even have to worry if it came from a normal distribution or not, if the population was normally distributed or not, because our sample is greater than 30. So we're good to go. We can apply the techniques, and we go ahead and apply them. If we're going to be 95% confident, just like we've seen before, that means that our alpha level is 0.05. So that means when we're looking for t, right, we're looking for a t of 0.025, because that's half of 0.5. We have a degrees of freedom of 49 minus 1, which is 48. If we're looking these things up in a table, the closest value is going to be 50. If you're using technology, you don't have to worry about that at all. This ends up being the t critical value that you get out of the table. So we're looking to see how our value compares to that. Plug everything in that we know. So we have the t critical, right? We have the standard deviation, the sample size, and we get 6.027. We then use our average of 0.4 and our margin of error of 6.027. We add and subtract that, and we get this huge, horrible confidence interval. That's a really big confidence interval, right? That's a swing of over 12 points. And you can also see that if mu represents the average change in cholesterol and our interval goes from both negative to positive, doesn't that mean the average change could be 0? Because 0 is in that interval. Doesn't that also mean that the average change could be negative, which, if we assume that this thing was set up properly, that means that their cholesterol actually went up? So what does this say about the garlic treatment? Is it effective or not? And hopefully you could look at those numbers and go, this is pretty much telling me that it's not effective, or at least the data does not support the claim that it is effective. Okay, well, now that we've looked at one example, you might still be asking, well, what the heck is this student t distribution, and why do I need degrees of freedom, and it's not a z-score anymore. What's going on? How is this different? Well, unlike the standard normal distribution, where our standard deviation is always 1, the student t distribution standard deviation can vary. It still always has a mean of 0, so it lines up like the z distribution that way. But the distribution changes based on our sample sizes. And the best thing to do is to look at a picture. So the orange one is the kind of distribution you get when you only sample 3 things at a time. Whereas the red one is what happens when you sample 12 things at a time. And then you can see that the blue one is the actual z-curve, standard normal distribution. So what's happening is, if you have a really small sample size, look at the tails. See how the tails are higher out here on both sides? So that means for small samples, you get more variability in the tail, and there's less clumping in the middle. It's a shorter, right? It's shorter in the middle and fatter out on the edges. So it's kind of been stretched out left and right. But as the sample size goes up, the distribution tightens up, and the tails get smaller, and the middle gets taller, and it ends up approaching the normal distribution. In fact, the theory behind this is when your sample size goes to infinity, the student t distribution ends up matching the normal distribution perfectly. And in fact, once your sample size gets above a certain size, it pretty much looks just like the normal curve already, but it has to technically go to infinity to match it perfectly. Just like before, we can find our point estimate for the mean, mu, and we can figure out the margin of error just from our confidence interval. If we're given just a confidence interval, like if we run this in technology in our calculator and all it does is spit out a confidence interval for us, we can average those two numbers to get x bar, which is our best point estimate for mu, and we can take the difference of those two numbers and divide by 2 to get the margin of error, our e, right, the plus and minus thing that we're adding to each side of our x bar. What if we want to work backwards like before and figure out how big of a sample we have to take in order to keep our margin of error below a certain size? Well, we just take that margin of error formula that we saw in a previous slide, solve it algebraically for n, and we get that ugly looking thing, which isn't so bad, right? We've got a z-score, which corresponds to how confident we want to be, right? 95, 90, etc., etc. We have to know the population standard deviation, and then we have to put in how big we want our margin of error to be. Well, what happens if we don't know the population standard deviation? Then, and before we talk about that, this is just talking about what we've done before, where whenever we're calculating these n's, no matter what the number is, if it's not a whole number, you always round up. So if it comes out to something 0.00001, you would still round up to the next number. Okay, that's what that says. So back to the discussion of what happens if we don't know what the standard deviation is. Well, we have a couple different ways of estimating them. We can use the range rule of thumb, which is take the range of your data, divide by 4, and that's roughly what the standard deviation is. It's a horrible estimate, but sometimes it's the best we can do. You can also start collecting data, calculate the standard deviation of your sample, and then use that as your best point estimate for the standard deviation of the population, and then calculate how big your sample size should be based on that. Go out, sample some more, recalculate as you sample, recalculate the standard deviation as you go, and if it changes your sample size, then you can refine accordingly. Or you can always just estimate what you think the population standard deviation is by looking at previous results. Maybe somebody has already collected some data in this area and they've already calculated a standard deviation, and you can use that as your best estimate. So let's say we want to estimate the mean IQ scores for the population of all statistics students, and we want to figure out how many students we need to randomly select if we want to be 95% confident that the mean that we get from our sample is within 3 IQ points of the population mean. So to be 95% confident, we look that up in the table if you haven't already had it memorized, and that gives us a z of alpha over 2 of 1.96. We plug in 3 for the size of e, right, because we want to be within 3 IQ points. And then the 15 comes from the standard deviation of the population that I guess we magically already knew, or we somehow got from one of those previous three techniques of doing the range rule, or from a little pilot study sample, or from somebody else's work. But we do all that, and it tells us we need to go and sample 97 people. Okay? Simple, easy. Now let's look at how we do some of this stuff with technology. Right? So let's go back up to this one here with those horrible numbers, right? That really bad interval that we got, and remind ourselves of what the data was. We had an N of 49, and we had a mean of 0.4 and a standard deviation of 21. So our N was 49, our mean was 0.4, and our standard deviation was 21. And we did all this with the formulas, but what about if we wanted to do it with technology? We'll start with the calculator. Go back to our stat menu, over to tests. We're still doing a confidence interval, but this time we're doing a t-interval, right? Because we're dealing with a t-statistic because we don't know the standard deviation of the population. Now it's going to ask you, do you want to do it with data or stats? Data would mean if you had the raw data. So you actually put these 49 pieces of data in list 1, then you would choose data, tell it list 1, and go from there. If you want to do it with stats, you choose stats, and when you click enter, it changes and it now knows what to ask for. So you arrow down and it asks for the mean, 0.4, asks for the standard deviation of 21, and that's just your sample size, so in this case 49. Confidence level we're going to leave at 95, and then we're going to calculate. And there is the same results they have here, right? They just rounded theirs more severely than we did here. And if we wanted to figure out E, we could do the difference between those two, divide by 2. If we wanted to find our X bar again, right, we could take the average, but we already have that right there. Okay, so that's in the calculator. Very simple, easy. What about if we want to do it in StatCrunch? Stats. Now we're doing t statistics, right? Because we're not dealing with proportions, we're not dealing with z's, we're dealing with t's. We have one sample. Again, with data as if we had all the data in one of our columns, under variable 1 or variable 2, and then with summary is when we just have the results. Our mean was 0.4, our standard deviation was 21, our sample size was 49. We're doing a confidence interval, compute, and there we have the same answers. Remember, standard error is not E, right? That's not your margin of error, that's your standard error. If you want to calculate your margin of error, you still have to do the difference between these two numbers and divide by 2. Okay, on to the second part of calculating sample means. In this section, we now know the standard deviation of the population, right? In the previous section, we were talking about how do we calculate or how do we estimate the population mean when we don't know the standard deviation of the population. Now we're going to estimate the population mean, still based from our sample, but we now somehow also know the standard deviation of the population already, but we're still trying to figure out what the mean is. Doesn't that seem kind of ridiculous? If we knew what the standard deviation of the population was, wouldn't we also probably know the mean? So this is a very rare case. You almost never know the standard deviation of your population without already knowing the mean. So this is more of a learning tool, and it does show up very rarely in the real world, but it is very, 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 very rare. Just like before, all the same stuff, mu, x bar, n, e, right? Except now we're back to z-scores, because now that we know sigma, right? Now that we actually know the standard deviation of the population, we can now use z-scores instead of the t-scores that we did before. We still have the same stipulations. Our sample must be a simple random sample. But now we have to know the population standard deviation, which we didn't know before. And like before, either the population that we're sampling from is normally distributed or our sample is at least 30, right? Just like before, we're estimating mu with some confidence interval, x bar plus or minus e. The only difference is now in our formula we're using z instead of t, right? Everything else is the same. Here's an example. We're seeing that boats and aircraft have been overweighted. So we're going to use the weights of men from a random sample we obtain, and we get that from our sample of 40, each man had an average weight of 172.55. Now, from several other sources, the research suggests, and this is where it's just kind of silly, that men have a standard deviation of 26. Well, if we had a bunch of other studies that told us what the standard deviation of men's weights was 26 pounds, don't you think they would have also told us what the average was, and then it would have been completely useless to have to go take our own sample? So you can hear the content in my voice for this procedure. It's just silly. But we'll continue on. Let's find the best point estimate for the mean weight of the population of all men. Let's construct a 95% confidence interval estimate of that mean weight of all men, and then let's see what that suggests about the mean weight of 166.3 that was determined to be the safe passenger capacity for water vessels back in 1960. Basically, when they figured out how many people could be on a boat, they calculated that based on the average weight of an adult male being 166.3. It's the same way that they calculate the maximum capacity of elevators. So here's how we would do it with our samples, right? We've got a mean of 172.55. We want to be 95% confident, so our alpha is 0.05, which gets us back to that 1.96 that we seem to see all the time. We can calculate E to be that 8.057, blah, 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 and we get this nice little pretty interval down below of that. Yay, yippee, awesome. Let's do it with technology instead. If we're going to do it with technology, we go back to stat, tests, only now, because we somehow know the standard deviation of the population, we're no longer doing a t test, we're doing a z test, right? Z of alpha. So z test. Sorry, I was already on it. Z test. Again, do we have data or stats? Data as if we had the raw data, stats as if we just have the results, which is what we have. Mu 0, that's the thing that we're, oh sorry, I'm doing a t-test. I'm a moron. We're doing intervals. Sorry. Z interval. Data versus stats, right? Standard deviation, you'll see how that's a sigma, not an S, so this is supposed to be the standard deviation of the population that we somehow miraculously know. And in this case that was 26. The average of our sample. You'll notice that this is 0.4 from our previous example. Your calculators keep the results that you did before, so you have to keep putting them back in as they change. 172.55. Sample size this time was 40. Calculate, same numbers they got, right? And if we need to do E, very easy to do so. StatCrunch, just as easy as before. Stat, only now we're doing Z statistics, one sample with summary. Same thing, plug in the 172.55. Standard deviation, I think it was 29. Sample size was 40. Compute. There we go. Okay, technology a lot easier than dealing with these formulas. How do we interpret our results? Well, the best point estimate is still going to be the sample that we get from the results we get from our sample. So the average of our sample is the best point estimate of 172.55. Look at this interval, 164.5 up to 180. The safety measures are based on a weight of 166.3. Well, is 166.3 in our interval? Yes, it is, right? Even though it's close to the left side, you still can't say, well, it's almost out of it. It is technically almost out of it, but it still is in the interval. So you really wouldn't be able to say with any level of confidence that this estimate of 166 is too low, but it's getting close. And since an underestimate would result in lives lost due to things being, overweight, this data would suggest they should probably kind of rethink their estimates. Okay, what did we look at for testing in this section? We had two key things. It was all based on, did you know the standard deviation of the population or not? If you do, right, if you do know the standard deviation of the population, which is very unlikely, you come over here, and is it normally distributed? Yes, you do a z-score, or if it isn't, but you at least have a sample greater than 30, you still do a z-distribution. If it's smaller than that, you do non-parametric stuff, which we don't even need to worry about that till much later. However, if you don't know the standard deviation of your population, which is far more likely, then as long as your population is normally distributed, right, or if it isn't but your sample is greater than 30, you come down here and you use the t-test. Once again, if both of those are no's, you're stuck with non-parametrics. So you can see you're stuck with non-parametrics in both cases. So you want to make sure that your sample is greater than 30, because then it doesn't matter what your population distribution is, you're always coming down to these two boxes. Okay, so just make sure you can sample 30 or more. T versus Z. T is what normally happens, Z is kind of the fantasy world, right? We do Z's when we know the standard deviation of our population, which is very unlikely, which is what I've summarized here. We use the Z distribution only when sigma is known and our other things hold, right? We use the T distribution when sigma is not known and our other things hold. And when those things fail, right, the population is not normally distributed and the sample size is 30 or smaller, then we just have to use non-parametric methods. Bottom line is, when in doubt, go with the T distribution. Most likely that's the situation you're in, because you only use the Z distribution when you know the standard deviation. So you better be given the standard deviation of the population, otherwise you have to use the T distribution. That's it.